a new module, module 2, analysis of algorithm efficiencies and the brute force method. Yeah, 2 parts. Yeah. First, part A. Yeah, actually we have part A, B, C, D. But today we cover part A and part B. Next time, part C and part D. Okay. Part A, problem solving from experience and elimination method. Yeah. 8.1, selection sort. So we will learn our first sort algorithm. Now, remember, at this point, we have learned one search algorithm, linear search, sequential search. Also, we learned one selection problem. Now here, selection sort, selection problem. That problem, finding the minimum. That's the selection problem. And here, our first sorting algorithm, but its name is called selection sort. Okay, all right, so let's start. Our problem number 5, sort an array. First, let me give you the question, given an array. Yeah. The question, how to sort it in ascending order. Yeah. I hear some noise. Yeah, so this is the general question, and in this class, we will solve the same problem at least 6 times. That means we will have 6 different sorting algorithms. This is the first one. At least 6. Could be more than that. Yeah. All right. The problem type, sort. Yeah. 3 basic problem types: search type, selection type, now sort type. Yeah. All right, I'll give you the reference in the textbook. Yeah. All right. Let's do analysis. Yeah. Remember the title, learning from the experience. When we need to solve this problem, we need to recall some related experience we have. Related experience. Yeah. All right. So that's module 1. Module 1 is our experience, our background knowledge. Okay. Yeah. Find a solution from our experience. So here you can see experience is important. Yeah. So we try to, expand our experience. If we have a lot of experience, then our problem solving skills could be better and better. Yeah. All right. Explore the properties. Yeah. So another step we commonly use, explore the properties. When we look at the whole problem, we need to study from different angles, and we try to discover many special properties. Here, given an array, we want to sort it in ascending order. You have many different angles you can look at this question. Yeah. Here, we try to explore some special property. Yeah. Okay. All right. So that's because these 2 things are very general, right? Not for this particular problem, for general problem. So our guidelines. All right. And here we also use backward thinking, another commonly used problem solving method, backward thinking. Okay. Yeah. So we assume, so what's the backward thinking? We assume we already have the whole array sorted. So then we do the, logical reasoning backward. Yeah. So that's another commonly used method. Here, let's try this way. Yeah. Question: if the array is sorted, what problem can we discover? Yeah. So we look at it in this way. We assume the array already sorted in ascending order. Okay, yeah. Here, for simplicity, we can assume distinct elements for convenience. In real way, we cannot assume, make this assumption. But in our solution, think about we can make our life easier. We can make appropriate assumption to make our life easier, right? Question.
So is the backwards thinking then like we're starting with the simplest possible like answer?
All right, so here it's different. Yeah, this different. Simplest. Yeah, when we get there, when we have a complicated situation, then we need to start with the simplest.
Okay.
Yeah. Here we haven't. Yeah, because here we try to discover some property. See, we want to look at the whole picture. If you look at a simplest case, one or two elements, then you do not have a global view. Your view is too narrow. Think about it. Suppose you only have two elements in this array. Although it's simple, but your view too narrow. You cannot discover property. Yeah, the property, not that obvious. When you have two elements, the property is not that obvious. So you don't want to simplify it. Yeah, here. It's a good question. Yeah. Sometimes we want to have a global view. Yeah, we don't want to make it very simple. There a lot of information missing. We couldn't discover. Yeah.
For something like this, like would an example of a property be the minimum, like the whatever element is the smallest?
Yeah.
It's going to be at position 0. Is that like considered a property of this? Like
Yeah.
for this specific problem?
Yes. Yeah, that's a property. Yeah. So yeah, pretty close to what you said. Yeah. All right. Question: how to connect this problem to the minimum problem? Yeah. Minimum problem. That's our experience. You know the minimum problem well. You know how to find the minimum problem. Okay, everyone here knows how to find minimum problem. So you can use that solution as the starting point. That's our starting point. Okay? Yeah. All right. Then do the critical observation. You need to find the main property, critical observation here. What's that? Look at it. So this ascending array in ascending order. Okay. How do you connect? Right now, this is the result. Backward thinking. That's the destination, the final state of the sorting. Okay. But can you connect this to our minimum problem? Then old solution can be used here. So that's the reason we want to connect. When you see that ascending order sequence, can you say something about the minimum problem solution? When you see the sequence, don't get into that detail. Yeah, the MISO comparisons, that detail we need it, but here, don't worry about that. Yeah, because we know, think about, you know the whole solution. You know the whole solution, so you don't worry about how to find it. Okay? You assume you can always find the minimum element for any array. Okay, so you have it. Then the question, the property, how do you connect minimum problem solution with our final state of the sorting problem? Relationship, yeah. Observation, yeah.
That each
Yeah.
step in the element is going to be the minimum subtracting
Yes.
the previous element.
Yeah, great. Yeah, simple, but that's the point. You get to the point. Okay.
Say that again.
So then if you have the array right here and you've identified the minimum element, if you remove that from the array and perform the minimum problem again, you're able to find successively each element in order.
Yeah, exactly. But I will, expand your description as a whole story. Yeah, and go through. So don't worry. Yeah. So because it's a big story here. All right. Now, here you can see the observation is very important. Yeah. So when you look at it, based on your understanding, so you make that critical observation. All right. That is A0 is the minimum of the whole array. A0. What's the A0? The first element in sorted array. That's A0. The first element. That's the same as the solution of the minimum problem. Okay? That's our observation. That's the critical property here. So we will take advantage of this property to complete the whole sorting algorithm. How about that? Think about it. Yeah, so let's do that. All right. The concept here, before we complete the whole story, I like to use this in place concept. Actually, just the meaning, easily. Here we say in this algorithm, matching your understanding in real world experience. All right. Here, we know when A0 is the minimum of the whole array, we should put it in the first position in our destination array. Okay? And that position is the right one, right? Correct. Correct one in the sorted array. So that position, right one, so we call that element is in place. We put it in place. Okay? That's just terminology. So later we're going to explain. Yeah. All right. Here, with this concept, can we say this? Given an array, original array, can we apply our minimum problem solution on the original array? Yeah, we can apply, we will get a solution, right? And here you use that A-1 comparison. Here you use that detail put here. Okay, all right. After we get that solution, can we put it in place? In the destination array, we just grab that solution and put it in place. Follow that. And after that, because one element is already in place, we do not need to worry about this first element anymore, right? In the remaining processing, we can ignore the first element. How about that? Yeah. So then, for the remaining elements, can we apply the minimum solution another time? We find the second smallest, and so on. In this way, can we solve the whole array? Yeah, so you get it. All right. So here, that's the definition. The element is placed at the position when the array is sorted. Yeah. Array is sorted, so there is a ascending order. That order, okay? In that ordered array, that position, if the array is at the same position of that place, it's in place. Okay, yeah. Now you can see the connection. Then now you can understand why we call the sorting algorithm selection sort. Because the main operation we apply here, the selection problem. Minimum problem is a special selection problem. Okay? So the solution of this sort is based on a solution of this special selection problem. So we call it selection sort. Okay, yeah. All right. And here we also use the elimination method. Although it's a simple version, yeah, but another time we use elimination method because after we put the first element in place, we can eliminate from consideration. The second one, we do not need to consider A0 anymore. We eliminate Okay? In that way, we reduce the problem size. The problem size get smaller, smaller and smaller. Then after we reduce to the last element, trigger. Trigger, nothing to do. Question? Yeah.
I was just gonna make some comment about how
Yeah.
long it would take.
Yeah, good. That's our next step.
Yeah.
How long? Because we need to consider the efficiency. Yes, won't be good. Yeah, won't be good. Yeah, this solution actually we can treat as the worst of
Yeah.
all we have. It's the worst. All right. Yeah. So, and yeah. So in each round, we place one element in place. We guarantee. Yeah. Every time we scan the remaining elements, we guarantee we can place one element in place. How about that? Yeah. Yeah. Think about until we put all elements in place, the whole array is sorted. All the elements in place, the array is sorted. But the last element, we don't need to do anything, right? When you have last element, you just put it right in place. Put it at the end. The last one then. The last position in the sorted array. Yeah. All right. Then now, so question. Yeah, here, actually, we already have that. Yeah, here, I just run this diagram to, to show the procedure. So the first time we find the minimum of the whole array, so we put that element in place. Okay. Then the second round, we only consider the remaining elements, ignore the first one, then we find another minimum element, we put it in place, and so on. Okay. Now, the last one, we don't need to do anything, we just put it in place directly. Okay. Now, so that's the whole procedure. Yeah. Conclusion. Now, yeah, so the first simple fact, right? That's a simple fact. When all the elements in an array are in place, this array is sorted. The simple fact. Okay. Yeah. But I like to, put it there to bring your attention. Yeah. Because later we may need to use this simple fact answer other questions. Yeah. All right. Efficiency analysis. Let's count the number of comparisons we need. The number of comparisons we need for this sort algorithm, for the best case, for the worst case, and for the average case. Let's answer this question. Okay, yeah. All right. Let's count the number of comparisons. The first round, n-1, backward, right? Backward. n-1, n-2, the last one is 1. Number of comparisons. Okay. Adding up, so the final expression for the number of comparisons is this number for the whole algorithm. Now, tell me, what is the best case efficiency? What is the worst case efficiency?
Best case would be that it's incidentally in order already, so every sort is just one comparison. That would be like our best case, or between sorts.
Anything? Say anything?
The worst case be descending order?
All right.
But
Right,
would be like n
Alright.
elements like is.
Yeah,
or n
it's possible.
for
I like
changing n.
It's possible.
But aren't we already comparing every single one? So
Right, every single one.
we don't have, our best
Oh,
case
yeah.
and our worst case, aren't they the same?
Same, yeah, that's the answer. Because even ascending order descent, you need to compare with everyone. When you find the minimum, can you ignore any of them? Yeah, when you find the minimum, although the first one is the minimum, but if you do not check all the remaining elements, how do you know there is a possibility some element at later position could be smaller? You don't know. So you have to do all the comparisons. So the best case, worst case, the same, then average case also the same, because you only have one case, right? Then you do average on one case, same thing. Yeah. So for this algorithm, we only have one case. Yeah, so the answer, the same thing, same number. Okay, yeah, all right. And here, I like to do a small summary on that elimination method. Because later, you need to apply this elimination method on several challenging questions. Now, actually, this week, next week, our third week, after next week, you need to have your first homework assignment. And then you will have a few challenging questions. Some of them we need to use elimination method. Okay, all right. The goal, reduce the problem size. When we do elimination, we reduce the problem size and make it easier. Okay, yeah. So the smaller the problem size, the easier the problem. That's the general fact. May not be always true. Sometimes there is exception. Sometimes the smaller size could be harder than larger size. That's possible. Yeah. Yeah. Because later, when you here, I can give you an example. Prime factorization. Okay. If you do prime factorization on some number n, the n value we treat as the problem size. N value, magnitude. Yeah. Suppose we consider n value 1,000, it's larger. Okay. When we compare with 357, which one easier to do factorization? Okay, the larger size could be easier, right? And the smaller one, prime factor, you need to, do some work. Okay, yeah. But this principle in general, correct, but always some exception. Always exception. Okay, yeah. All right. When some elements do not change the outcome, yeah. If we know after we do some work, we find certain elements cannot affect the final outcome, so we can comfortably eliminate them from the configuration. But if you are not aware of this, you still keep those, useless elements. We could say useless element in the group. Then you may do redundant operation. If you put useless elements there, you may put some redundant operation. You waste your operations. Okay. Yeah. All right. So that's the